sun shines down on my bright white shirt. Because my shirt is bright, it reflects most of the light that hits it, and I stay cool. Now the sun shines on my dark black sweater, and it absorbs most of the light that hits it, and I start to get warm. What if I told you that ice could act like this and like this? Say there's a planet orbiting the sun with some bright white ice at the poles. Most of the sun's light is light that we can see with our eyes, visible light. Ice on that planet is going to say to the sun's light, okay, thanks, but no thanks. I appreciate the sunlight, it's keeping me warm, but I don't want to be that warm, okay? Light is energy, it's heat. So I'm going to take a little bit of your light and give you the rest back, okay? I don't want to melt, I want to grow. And you know what? I get my wish. The more sunlight I reflect back to space, the less sunlight I absorb. The colder the planet gets, the more ice forms. Pretty soon, without carbon dioxide or some other greenhouse gas in the atmosphere to keep the planet warm, it'll become covered in ice, a snowball. But here's the thing. Ice doesn't treat all types of light equally. So everything with a temperature glows, but not everything glows in light that we can see with our eyes. Us, humans, we glow, but we glow in infrared light, not visible light. And so do stars that are cooler than the sun. They glow in infrared light. Ice on a planet orbiting a star that's much cooler than the sun is going to say something different to its star's infrared light. It's going to say, come on in, baby. I want you. I need you. I have to have you. Don't worry, baby. I'm not going to reject you and reflect you. I'm going to absorb you. That's how much I love you. And the more infrared light that ice absorbs, the warmer that planet gets. Remember, light is heat. The warmer that planet gets, what's going to happen to that ice? What's going to happen to it? It's going to melt. So the take-home message is this. If you have a planet orbiting a star like the sun or a brighter star, and not much in the way of greenhouse gases in the atmosphere, ice could grow really fast on that planet. If you have a planet orbiting a much cooler star, ice might never grow, even at the poles. Ice is tricky that way, and very powerful. Thanks.
Judges.
Well, that was great. Very nice, natural use of gesture and humor and great delivery, really interesting content. This is your own research bears on this. Is that true?
Yeah.
It's not just something that somebody knows in some disembodied way. So the one thing I would have maybe like to see you add was let people know that. You know, I have discovered, I have done research which shows, because in a sense you're almost being modest here in that you know, you're an astrobiologist who studied this, and the fact that we know this interesting stuff has something to do with the work that you yourself have done. So if there was a way to work that in a little bit, I think it would have been really cool. But you know, you're a natural and you did a great job.
Thank you.
Completely agree. I thought it was great. Good explanations. I like the way you engage with the audience. My only, you ended on ice is powerful, and I just didn't know why.
Okay.
So it just kind of left me with a question. It was a little frustrating, but it was a great job.
I also thought that you did a great job. I think that it's very cool when you walked on stage and we had no idea that your costume, that your clothing was a costume, that you had chosen to wear black and white specifically for your thing, which is, that's what she wore that day. So that's always a nice surprise. You go, oh, well, that's pretty cool. And I think that you, your questions, most of which were rhetorical, but one where you actually expected an answer from the audience was very nice. And it also was something interesting to think about, and something that most people hadn't thought about, but for the lay public was in their zone where they could understand it. There are plenty of things in science that are interesting to think about, but you need like 25 years of research to even know what that is. and you picked a topic that was familiar but a different spin on it. So I thought you did a great job as well.
Thank you. We've discovered over 750 planets orbiting stars other than our sun. And with all this talk about new planets comes a lot of talk about a star's habitable zone. That's the region around a star where liquid water on a planet's surface would stay just that, liquid. Too far outside a star's habitable zone and all the planet's oceans freeze. Too far inside and all the water boils away, like water in a pot you leave too long on the stove. But a habitable zone is a fluid, changing thing. A star brightens as it ages, sending more intense radiation out into space, pushing that region where water can stay liquid on a planet out farther away from the star. The same way I have to scoot back from the space heater that I turn up on cold Seattle nights so I don't get burned. Planets could have more carbon dioxide in their atmosphere than Earth. And if so, they could experience a greenhouse effect like nothing we've seen, and the oceans could still boil away, even if it's technically in that Goldilocks zone for liquid water. Not too hot, not too cold, but just right. But wait a minute, we're assuming that for life to survive on a planet, there must be liquid water on its surface. Is that true? There was a time, 700 million years ago, when our planet was covered in ice from pole to pole. There was even ice at the equator, and yet life survived. Even photosynthetic life survived. Green algae that uses carbon dioxide and sunlight to make oxygen, oxygen that we humans would eventually use to breathe. Green algae survived the deep freeze. Jupiter's moon, Europa, has a thick ice crust far outside the sun's habitable zone. But spacecraft tell us there's an ocean beneath the ice. Saturn's moon, Enceladus, spews geysers of liquid water out into space. It's literally Yellowstone's Old Faithful in space. Could there be life on these worlds? There's certainly life at Yellowstone. In fact, on Earth, anywhere there's water, there's life. So the next time someone asks you where else in the universe we should look for life, don't just think about what's on the surface. That's like looking around the house for milk without opening the refrigerator. Think about what's lying beneath, or else we may miss out on discovering that we are far from alone in the universe. Thank you.
I thought that was great. I really liked your enthusiasm. I liked your energy. That was a terrific little talk there. I have a question. How do you figure out where the habitable zone is on distant stars? In other words, around Earth, we know there's liquid water on Earth. We know it's on Mars. We know it's on Venus. But a little dot in the sky, how do you figure out where a habitable zone would be around that?
Yeah, great question. So usually the traditional limits of the habitable zone are where if you're too far out from the star, carbon dioxide is going to freeze out of the atmosphere. So it's actually going to be a solid. Carbon dioxide will become ice. And then the other limit, the inner limit, is where you actually would lose all of your water to space in the atmosphere. And so we can figure out, based on the radius of the star, how large or small the star is, how much light it's sending out to us. We can measure that from telescopes and other instruments, and we can figure out how far away a planet, a hypothetical planet, would be in order for those two things to happen. And that way we can tell, okay, right in the center is where that Goldilocks region is, where we don't have water being lost to space and we don't have carbon dioxide freezing out onto the surface.
Great. I thought your energy, just like this morning, was great. It's clear, it's concise, your passion is there. So speaking about your passion, tell us just very briefly, why water, why space for you?
Why water, why space?
Mm-hmm. For you.
For me. You. Well, gosh, when I was 12 years old, they showed a movie called Space Camp to my 7th grade class, and I fell in love with the idea of becoming an astronaut. And so at that moment, that was, I'm going to belie my age here and say it was 1986, And no, it was actually 1987. Oh well.
We'll figure the year out.
That's when I realized that I wanted to learn everything there was to know about astronomy. And now, since I've come back from kind of circuitous route in my career to astronomy, there's this great new field called astrobiology, and it's all about looking for life elsewhere. And when we talk about life elsewhere, the first thing we say is follow the water. Where there's water, there's life. Those are the two things that we can connect, at least here on Earth. And that's really the only thing we have to go by, is what here on Earth, what does life require here? And that's where we're going. We may find out that life can need very different things than life needs here, but we're going with what we know. And so that's why water, why space.
Great job.
Thank you.